We're talking about relations and functions. A relation is a relationship, and it can be any kind of relationship between a pair of numbers. And it can be represented in a couple different ways. Actually, there's 5 ways to represent. I should fix that. And then number 5 would be an equation, but we're not going to work with those just yet. We can represent a relation as sets of ordered pairs. And all it says is that 1 goes with 3, 5 goes with -2, and 0 goes with 5. It's just any kind of random relationship. It doesn't have to be a pattern that we can see for it to be a relationship between numbers. We can do a table. 1 goes with 3, 5 goes with -2, 0 goes with 5. We can do a graph. Okay, I can do 1 goes with 3, so I put a point on the 1 and for the x and the 3 for the y. 5 goes with -2, and 0 goes with 5. Okay. Or we can do what's called a mapping. Now, mapping, we create 2 rectangles. The first rectangle are our x's, the second rectangle is our y's. And we draw an arrow to show which numbers go together. So 1 goes to 3, 5 goes to -2, 0 goes to 5. Yeah, I should say that. I'll put that down here a little bit better. Okay, we can represent relations with equations, but not all relations. So this particular relation cannot be represented with an equation. At least not one that I can think of off the top of my head. There might be some freaky, natural log or something that will give me these numbers, but off the top of my head, I'm not thinking of anything. But that's just another way that a relation can be represented. It's just not this particular relation. But at first I had said there were 4 ways to represent, but there's really 5. I didn't want to leave off the equation just because we're not doing it right now. All functions and relations have a domain and a range. Okay, the domain is all of the x values. And this can be finite, so we can have a list, or it can be infinite. So we could say something like, x is greater than 5. So it would be every number that was greater than 5 could be our domain. Okay, so your domain can be finite or infinite. And it's all your x values. Now your range then is all of your y values. And again, it can be either finite, giving me a list of y's, or infinite, giving me, y is less than 0 or something. Or it could be, all real numbers. From our last relation, I had, I forgot, 1, 3, 5, -2, 0, 5. So 1, 3, 5, -2, 0, 5. And we'll come back to our mapping. Now, in our example, I listed the rectangles as x and y. When you do a real formal mapping, it's the domain and the range. So our x's are our domain, and our y's are our range. And what happens is the domain, this is the input, and this is the output. So the way it works is if there's some sort of like magical relation box and I throw a 1 into it, I get a 3 out of it. If I throw a 3 into it, I get a -2 out of it, and if I throw a 0 into it, I get a 5 out of it. So the domain is what numbers you plug in, the range is what numbers you get out. And we're going to express it as a table, a graph, and a mapping, because it's already being given to us as a list of ordered pairs. So for our table, we just make an XY table. We list our x's. Now,
Do they need to be in order?
I'm going to put them in the order that they came in, just like this. Now, when you have a table, you list all of your ordered pairs because this is saying 2 goes to 5, -2 goes to 3, 5 goes to -2, 1 goes to -2. And when you have a graph, you plot all of your ordered pairs. But when you have a mapping, that's a little different. What I do is I'm going to make my domain and my range. You're going to list each x and y once only. Okay, so if you have any repeats, you don't list the second or third one. You only list it once. So in x, I have 2, -2, 5, and -1. For y's, I have 5, 3, -2, and then -2 again, but I only list it once.
Right.
And then when I draw the arrows, I'm just going to have 2 arrows going to it. Now this will come in handy later when we're trying to identify functions. But the reason we're doing this is because this is the set of all of the domain elements, this is the set of all the range elements, and -2 is itself, so we don't list it twice. That's just like I wouldn't list any one of you twice in the classroom. You're only yourself, so I wouldn't list you twice. Does that make sense? Okay. So that's the only time you have to do that, though, is on the mapping. On the table and the ordered pairs, on the graph, you take care of all of them. It's just the mapping that you only list things once. So for the graph, I've got 2, 5, so that's this point. -2, 3, 5, -2, and -1, -2. So as you can see, this is not a straight line by any imagination. We want to list the x's and we want to list the y's, but we only want to list each one once. So the domain is 2, -2, 5, -1. And I usually just put brackets around it or braces. And then the range is the y, so 5, 3, -2, and then -2 is again, so we only list it once. Because each number is just itself.
Is it fine if you just like do it in the box? How you did it?
The bracket? Yeah, that's fine. Yeah, brackets or braces is fine. Domain. Range. And we had -3 already, so we only listed the once. And we have what's called independent variables, and the independent variable is the domain, which is the x's, which is the input. Okay? The independent variable is the variable that we can pick. Okay, so like we can pick it, or it's a variable that we have no control over. And by that I mean time. Time is going to pass whether we want it to or not. Time is independent. Do you guys all agree? Time independent? So the independent variable is the variable that either we can choose the number or it's a number that we have no choice over, like time, because time will continue to pass. Unless we had a TARDIS, but unfortunately I don't have my TARDIS. I've tried to order it, but they don't deliver. I don't know what's going on. Okay, the dependent variable, that's the range. So it's the y's. It is the output. Now the dependent variable depends on the independent variable. Okay. So this one is the one that must be figured out. We can't choose it. Does that make sense? All right, so when we want to talk about which variable is independent and which variable is dependent, we start looking at scenarios. Okay, the dance committee is selling tickets to the fall ball. The more tickets they sell, the greater the amount of money they can spend on decorations. So our variables are tickets and money. Which one depends on the other?
The money depends on, the ticket depends on the money.
Opposite. The money depends on how much money they raise, depends on how many tickets they sell, right? So the more you sell less tickets, you have less money. You sell more tickets, you have more money.
Right.
Does that make sense? So ticket sales, that's going to be the independent. It's either we've chosen it, or in this case, it would be something we have no choice over because people are either going to buy the tickets or they're not, right? So we don't really have any way to control how many tickets are sold. So that's the independent variable. And then the money for decorations, that's dependent because how much money we have depends on how many tickets got sold.
That would be the fifth, right, though?
This would be the fifth. Yeah, this would be the equation. So we could represent this relation if the tickets were $4 each. $4 times the number of tickets sold would give us the amount of money we have.
How do we know if the tickets were $4?
Oh, I'm just saying,
Oh,
like, it will be given to you. I wouldn't
Oh,
expect you to just magically know that. No, we're just hypothetically, if the tickets are $4, then to find out how much money you had, you do 4 times X to get the Y.
Right.
So the input is the X and then the out is the Y.
Right.
Does that make sense? Okay. So this would be the other way we could represent that relation, is with an equation. Okay, the average price of going to the movies has steadily increased over time. Independent variable? Well, which one do people have no control over?
The price of the movie ticket.
No, somebody has control over that.
So it's steadily increasing over time? Or
Time. Time is independent. Time is always going to be your independent variable. If time is mentioned, it's the independent variable because we cannot control time. Time passes. We can't stop it. We can't reverse it. Time is extremely independent. It just does what it's doing, right? So in this case, the dependent variable, the thing that is changing because time has changed, is the cost of the movies. So back in my day, back in 1821, just kidding. No, back when I was young, like when I was in high school, we could go to the movies and it was like $2 for a ticket, maybe 3 at the expensive theater.
In Puerto Rico, the movie tickets are $4.
Yeah, okay, so yeah, it was like that. But now, it's like, I don't know, what is it to go to the movies today? Like $500 for 2 people to go to the movies and buy popcorn?
If you go in the evening time, it's like, and you get the good screen, it's like $12.
Yeah, see, so it's increased over time. Time is the independent variable because time has passed. Movie prices have gone up because time has passed and inflation and all that stuff. Analyze graphs are also relations, right? That's okay. So we can analyze the graph, right? So, oh, I lost my word. There was a time here. Okay, so what's happening is Francesca's going on a bike ride, and as time is increasing, we've got distance increasing, so we can analyze the pattern and the shape of what's happening here. So in this portion of the graph, she's increasing. So like the first part, her distance is increasing, so she's riding her bike, right? And then here, time is passing, but the distance isn't going up, so she stopped for a bit.
It's like that means that she stopped?
Yeah, she stopped. She's not riding her bike anymore because her distance isn't increasing. So time is still passing, but she's no longer increasing in distance. So maybe she stopped to get a drink of water, maybe she stopped to talk to somebody, but we just know she stopped.
Right.
And then in the third part, she's riding again. Now, we can't tell how fast she's riding. We don't know any details about where she's going. We can only analyze whether or not she's moving. Okay. In this graph, we have 1, 2, 3, 4, 5 sections. See that? Like 5 different kind of areas where things are happening. So we start out, we're driving, and then we go flat again, so we stop. Yeah, maybe it's a red light. And then we drive. And you know how this one's like a little flatter than these? Do you see that? These are kind of really steep, and this is kind of flatter. So we're driving slower, yeah. And then we stop again. And then we drive faster. Did everybody see how I got that?
Yeah.
Not too bad. Okay. Then here we have 1, 2, 3, 4, 5. Again, 5 sections that are happening. And over time, our income is increasing, so money is going up a little. And then we had like a really sharp increase, so money went up a lot. And then this one's not quite flat, but it's really close, so money went up not much at all. I should probably number these. 1, 2, 3, 4. And then on 4, money went up a lot again. And then on 5, money just kind of went up like steadily. Does everybody agree with the interpretation there?